Next-gen anchor design is about harnessing whole-life seabed evolution modeling using probabilistic surrogates. This project is supported by the Supergen flexible funding and Royal Academy of Engineering. It brings together expertise in geotechnics, mooring systems, and extreme loads, and builds on previous work by all of us. So during our previous work, we showed that anchors like this pile or these plates can be made smaller if we can better capture the loading and soil response in our design approach. This approach is also all aligned with this plan, the IGP, which highlights that moorings and anchors are important for the UK as a potential industrial strength. So the UK is targeting up to 100 gigawatts of offshore wind by 2040 and 120 gigawatts by 2050, with floating offshore wind to generate more than a third of this capacity. This will require the manufacture and installation of at least 1,000 anchors on average per year, which is well beyond current supply chain capacity. Next-gen anchor design aims to contribute towards this challenge by reducing the cost of anchors through developing a fully probabilistic framework for anchor design, which unlocks more efficient anchor designs that involve smaller and lighter anchors. The challenge is that traditional anchor design is based on oil and gas practice and involves large anchor sizes that are not feasible for commercial scale floating offshore wind farms. This is because traditional anchor design involves conservative safety factors to account for uncertainty in the loads applied, and this tends to be factored up, and the resistance provided by the anchoring system, which tends to be factored down. However, whole life geotechnical design is an emerging concept which could lead to more efficient anchor designs. This is because it takes into account the evolution of seabed strength, and so anchor capacity, which can rise over the operational lifetime of the facility as a result of seasonal variation in the loading applied to the anchoring system. But to know how much smaller we could make our anchors with known uncertainty requires two things. The first is the accurate generation of metocean conditions and anchor loads over the operational lifetime of the facility. And the second thing is the ability to track the changing seabed strength and anchor capacity with time. To do this, our approach has been to create a probabilistic design framework which uses a surrogate model that can rapidly generate many realizations of anchor loading history for a 15 megawatt floating offshore wind turbine modeled in Orcaflex as a function of environmental conditions, so wind and wave conditions. So we have used statistical representations of metocean conditions to select discrete sets of wind and wave conditions, to then apply and run in simulations of a floating offshore wind turbine, to then create a training data set of anchor load time series for our surrogate model. And then we have combined this surrogate model with a seabed evolution anchor macro model that we have developed to allow us to explore probabilities of failure for different anchor sizes, and so identify optimal anchor sizes with known probabilities of failure throughout the operational lifetime of a floating offshore wind turbine. So, to model peak anchor loads, we focused on capturing the tail of the peak anchor load distribution, as this is the region of interest for extreme loads, and we used a peak over thresholds method to do this. We also used artificial neural nets to help us to fit the generalized Pareto threshold parameter, shape and scale parameters, as well as the occurrence rate of the peak loads over a 1 hour simulation. Preliminary results shown here showed pretty good predictions between the probabilities of peak loads between the surrogate model and the anchor loads from Orcaflex. So each gray line in this plot here represents an hour-long simulation, and the red line is the aggregated trend, which doesn't lie so far away from a one-to-one line. For the cyclic anchor loads, we used artificial neural nets to fit the probability distributions for cyclic mean load cyclic amplitudes, and the average number of cycles over a 1 hour period. Here are some preliminary results that show that the anchor damage equivalent load predicted by the probabilistic surrogate is on average not so different from the anchor damage that we calculated from the Orcaflex simulations. You can read a bit more about our work in these papers, which will also be presented at the OMA conference in Tokyo later this year in June. So bringing all of this together, this means that we can predict the probability of anchor failure for different anchor sizes over a 20-year operational lifetime. So for example, for a probability of failure of 10 to the negative 3, we would need a minimum anchor size of 7.5 meters. And the results here give us the ability to determine how much smaller we could possibly make our anchors compared to the traditional anchor design method by taking into account whole life seabed beneficial effects. This is ongoing work, and the outputs of this project will include a code and database with documentation on how to train and use the surrogate model, as well as include examples of how to use the probabilistic framework for efficient anchor design. So watch this space. Thanks, and please reach out if you have any questions.